Okay, so now let us start. This is the chapter where we are. So we finish our hardware part, we finish our assembler. So every group, you can do your group project. So there's no problem. If you do the group project one, now it's totally clear. Everything is has already been done. So if you do group project two, so you can also start. So it's not related to assembly, so it's more likely the scheduling. So today we will do one chapter. So this one is a virtual machine. Before we do virtual machine, I will write something is okay. We have the hardware stack. So this one is all hardware. Machine learning is a kind of intermediate, actually. It's between hardware and the software. So machine language can be accepted by the hardware directly. So you can treat like the portion of the hardware to let the hardware works, let the hardware work. But it's also related to the software part. For the software part, machine language is the last portion. Okay, so chapter 6, we have already do the assembler. With just announcement, you have one homework, deal with machine language. So use a CPU emulator. So I have already posted the homework on the Blackboard. When the class finish, you can check the homework. We finish assembly language. We use assembler to translate from the assembly language to the machine language. And assembly language, sometimes we call it a symbolic language. So symbolic, why we call it a symbolic language? Because it's mostly like a machine language, but I just add a certain kind of variable name instead of the number. And we have certain kind of command to help you to remember instead of you just remember 0, 1, combination of 0, 1, you can remember a little bit easier, like you can do plus, minus, this kind of easy understanding, you can easily remember those language. So this is assembly language. Okay, so quite similar to machine language. Machine language is just a binary code, and assembly language is just a symbolic version of binary version, right? So, but assembler do a little bit extra because you have certain kind of control or the label. So you should convert the label to the number. You should convert a certain variable we discussed the last class. Still remember we have at I or at summation. This one you can convert to the number. Assembler will do this extra. But actually it's not do much extra, like we want to add from 1 to 100. You still need to write plenty much of code to achieve this procedure. Then we need some way to make it even easier instead of just write the code in assembly. So we call it high language, okay? So the high language is the very common, everyone have already learned Java. So Java is one of the high language. Of course, you will learn C++. So C++ is also high level language. In terms of this portion we see, this is also high language. Although you will maybe learn sometimes C or even higher language, Python. So this one is a high language. So from high level language to assembly language, we should have some way to convert. Because your high language is that high, for example, if I want to calculate from 1 to 100, you just need a very simple code to say for integer I, so integer I equals to 0. I don't write more. So if it's in Java, so I equal to, or maybe it's start from 1, then I smaller than or equal to 100, I plus plus, then summation plus equals to I, right? So you finish. But assembly language you write plenty much. So we should have a way to convert from the high language to assembly language and then use assembler to transfer to the machine language. But this conversion, we call it a compiler. We call it a compiler.
11
So,
Pro Max in the middle.
Excuse me, any question?
Max है ना 11 Pro मत.
Okay, so we need a compiler. But when we look at
मलाई
the
गर्दा हो iPhone 11 गरौँ.
मैले women भनेको कि यहाँ
Excuse me, Ramesh, do you have any questions?
Oh, sorry.
Okay, so we will need some way to convert high-level language to the assembly language. And this is our level. So we have, this one is more likely high-level language. So this is, and our final goal is try to compile your high-level language to your assembly language. So this one, high-level language, actually, what we do is just multiply x and y. So this one multiplies two numbers. Since our assembly language does not support multiplication, so I need to write the function. So later, when the assembly, the compiler see this one, it will directly do the multiplication, and you can call multiplication. So something related to this high-level language convert to the assembler. So the first thing is we should be able to, the things is, we should be able to evaluate our within the function. So we should arithmetic. So for example, I should be able to let it able to understand the while loop. So the compiler need to do is understand how to do this result equals to result plus x, and let j equal to j minus 1. It should be able to convert this one to the assembler, to assembly language. So the compiler should first need to know how to analyze your arithmetic calculation, like result equal to result plus x, like j equals to j minus 1, this kind of thing. And the second one, the compiler should be able to analyze this while loop. So not j equal to 0. So it should be first do the comparison between j and 0. It should also need to do how to do the not version. So this one is the logical expression. You should be able to understand. For the compiler, should understand, okay, this is the logical, and give the true or false as the output. Maybe just 0, 1 as the output. So this one is the compiler should understand. Okay, so compiler first need to know how to deal with the arithmetic expression. Then compiler should need to know how to deal with the logical expression. And then the compiler should also know how to deal with functions. Because the major things different from our high-level language and assembly language is we allow the word high-level language to create the methods or create the function. So you should be able to call this function. So like this, you should call this function. So from here to here, and you should be able to process the function. And also you should be able to go back from the original calling. Okay, there's three things the compiler should be able to handle. Call the function, process the function. Most of the time is arithmetic and logical expressions, and then should correctly return the result back. Right, so this is the function calling. Of course, for our Java, C++, you have another thing is objects and instance. So object and instance should be also considered by the compiler. So this one is treated like a big functions, but you separate the variables like this is local variable or this is related to this object or that object. So this one is associated with objects. So in summary, I think the functions, the compiler, let me see, so should be do this kind of thing. So there's four things. So one is arithmetic Boolean commands. You should be able to do that. And you should be able to handle the memory because you will do, you should store your intermediate results. And you should be also do, probably next week, we will do the program flow control. So like the while loop, like the for loop, how do I declare? How do I use the label if go to do this program flow command? And as well as the last one is the most complicated one is the function calling method. You should be able to call the function, process the function, and return from the function. Okay, so far so good. Sorry. Okay, so before we do it step by step to convert this full portion, we still need to do one more thing for the compiler. So the compiler, what we should do is we have a lot of hardware platform. For example, you have Intel platform like x86. So this is one thing. So you may, what kind of platform you can have? Okay, you can have x86. So this is more likely Intel IBM computer. You may have some kind of things called embedded systems. So you may have some embedded. Most famous one is ARM, ARM. So ARM, embedded systems. You may have other stuff like you may have, for example, our hack machine, different platform, right? We have this, we have a hack machine. You may have Raspberry Pi. This is also like an embedded system, but you can also let it to be a small computer. So this one is different types of computer with different types of hardware. Okay, and probably you will have a lot of hardware assembly language associated. So different platform, different hardware. Okay, so this is one side from the hardware part of side. From the software part of side, how many software language you can have? Okay, we can have Java, we can have C, we can have C++, Python, Ruby. Okay, so that many language, Fortran like that. So what does it mean? It means that we should consider, if we don't consider clearly, picture very clearly. So this one is okay, high level language, I have N language. Then I have different hardware platforms. So we have platform 1, platform 2 to platform M. Then if I have this much and we create the compiler, then our compiler will need n times m translators. So this one means your compiler should have n times m version, different version, one language to one hardware. Okay, this is tremendously too much. Tremendously too much. Because when I create one types of language, then I need to create m number of compiler so that it will compile my code to different platforms. Hey, this one is very, very headache. So this one is directly compilation. So the compiler will do directly. So this one is not good. What we want to do is, okay, why not we consider another way? And we have some kind of, we call it intermediate language. Okay, this intermediate language will abstract all the hardware platform information and provide APIs to the high level language. So here through API, hardware language will just call certain kind of API to process on the intermediate language, and the intermediate language will hold, say that, okay, through this API, I will implement different platforms. So this API may have different versions, or it may have different implementation for different hardware platforms. So when I create one high-level language, I only need to know when I want to process that, I call a certain kind of API provided by the intermediate language so that I don't need to worry about the hardware anymore. But if I'm the hardware platform, if I create one hardware platform, I just need to provide the intermediate language a certain kind of implementation. I just redo all the API in the intermediate language to satisfy my own hardware platform. So this implementation we call the two-tier. It's not a one-to-one compilation. It will be two-tier compilation, and which requires only n plus m translators. So this one is need n translator, and this one needs m translators. Here is m, here is n. So it will save me a lot from n times m to n plus m. And this one, this two-tier, we only need to worry about the first tier is the stage, depends only on the details of the first tier is here. So it's only depends on the details of the source language. So it's a high-level language. And the second compilation stage depends only on the hardware details. So the target hardware. So then I can separate this and save my time. That's why instead of teach you compiler directly, we separate into two-tier, and this machine, we call it a virtual machine. Okay, so this intermediate one is called a virtual machine. So the intermediate code, the interface between the two compilation stage. So the first one, then here we call it, we need a compiler. So you will see compiler, compiler, compiler. So this is called, this side is called a compiler, and this side is called a virtual machine implementation. So virtual machine implementation, virtual machine, virtual machine, virtual machine. Okay. So this is the virtual machine, and this guy is the virtual machine. This is a virtual machine, means it's not related to any kind of platform, but it has very close to different platform. It has the knowledge of every platform. And compiler side it will only deal with virtual machine and ignore the specific requirement of the particular platform. Okay, so this is the big picture of compiler. And actually, here the whole thing, we call it a compiler. Whole thing is a compiler, but sometimes we do the specific. This one is the compiler, and this one is the virtual machine implementation. Okay, so any questions? Okay, so now, then we just generate. So we move forward. Now our compiler issues will separate two parts, and then we just need to sufficiently generate to support many high-level language and machine language pairs. So this one is our stuff. And language of an abstract virtual machine, and then this one is the intermediate code. It's the virtual machine. So anyone can give me some examples of the virtual machine you have already know? You have already known? Yeah, good. Java virtual machine, right? Java virtual machine allows you to eliminate any kind of platform. So you just work on your Java source code, right? So you don't need to worry about what is machine you are working on. So you can work on the Mac, you can work on the Windows-based stuff, or CPU, Intel CPU or AMD CPU, doesn't matter. So this one is Java virtual machine. Yeah, good example. So thanks, Destin. Now, our computer organization, we will finish at these two chapters, chapter 7 and 8, to focus on the virtual machine. And for the higher level, we will move to the operating systems, which will introduce the high-level compiler as well as the high operating systems. So our stuff is try to learn the virtual machine, and the lecture plan is this guy. We just do it. So this lecture, we will do this arithmetic and boolean command. Okay, together with the push and the pop. Pop action means pop the value from the stack to the memory, and the push is being a variable or a constant. Push y being a variable or a constant. So you push values from the memory to the stack. So this is memory access commands. You will see we use pop and push. Pop and push. Everyone finishes data structure, right? Okay, you probably know that in the data structure, you should push and pop. What does it mean? We want to use what? What the data structure we want to use? No, not queue. Yeah, stack. Okay, stack, we use pop and push, okay? Okay, so let's forward. And this lecture, we will focus on this one. And the style is, since you finish data structure, so the style is I give the problem and let you try. And try to review your stack operation. And next week, we will deal with our program flow commands. Probably you will do the loop, do the if-else statement, And we do the function calling. So function calling is the most headache one. We will do a lot of actual work for that one. So this week, it should be a little bit easier than the next. Okay, so VM model and the language. So I just briefly do a little bit of view one. The VM is a machine that makes sense in its own right. And the view two is the virtual machine is a convenient in-between representation of a computer program and the intermediate station between the high-level code and the machine-level code. So you can treat it like both is okay. But that's why most of the time, sometimes you will, when you deal with Java, we say the Java virtual machine is more likely is the machine. We treat it like a machine. But actually in the program, you can see is in the, it's an intermediate language between high level and the low level. So we have a lot of other virtual machines. So now, briefly overview of the stack. Okay, stack, usually you have the bottom. This time our bottom is on the top. So if you do, this is the stack pointer, means it points to the next available free space here. So this is the stack. Okay, this is free. Okay, nothing. So now I want to process add, means I will pop two values. So I will let SP plus 1 plus 2. So to get these two values and add them together and push it back to the stack. So finally you get 9 here. So pops topmost values X, Y from the stack and computes the value. Typically operation is computes the value of some function f, x, and y and push the results onto the stack. So this is a little bit different from when you do the data structure. Your data structure always look like stack as this. Okay, so your stack is always looks like this and your pointer is at here. So maybe sometimes some textbook, the pointer is the put to the last element. So point to the last element. Some textbook will say that, okay, the pointer will be on the empty one. So which one do you do? I think this one is more common. So this is 1 and 2. So 1 is more common because it's very convenient, because this one at the beginning, your initialization, then your pointer will be at here. So it will be quite easy to implement. So most of the time we will do this way. So, but in our slides here, it's just upside down. So just mention a little bit. Okay. So in general, all arithmetic and Boolean operations are implemented similarly. But now, so our virtual machine for the hack machine is a single 16-bit data type that can be used for integer, Boolean, and a pointer. So you can put a pointer there. Later, when we do the function calling, then we will also put the pointer in our stack. So don't forget this one. This one just wait for a while. We will do later in the next week, at the next week. Today we will do two things. One is the integer, one is the Boolean values. So, okay, now we can also use push and pop to access the memory. So for example, before my program stack has this 3 values and the stack is here, and we have the memory address, 1 is A, 1 is B. So I want to push B. What does it mean? It means that push means you push the items into the stack. So push B means you want to get the value at the memory with address B, such that here is 108 and push this value into the stack. So when you finish this push B, it looks like you will do 108, move 108 from the memory, not actually move. Actually, it means copy 108 from the memory to the stack. Okay, to the stack. This is push. How about pop? Pop A. Pop A means that I will put the value at the top of the stack and remove this one. This time it's move to A. So when I finish this operation, this is okay. I pop the value 17 in here. So this one will be removed and the stack pointer will move to here and pop this value 17 to the memory address at A. So memory address is A and put the value there. So after my operation, then 6 is disappear because it's overwritten by 17. And the 17 is moved out from the stack. So look at this push is a copy to the stack. Okay, here is move out 17 out and then put at the address A and replace overwrite 6 at overwrite 6. Okay, so this one is a very classical data structure, push and pop. So you have already learned in the data structure. Now you see the usage in our computer organization when you deal with the arithmetic evaluation. So any questions? Okay, now I want you to do this work to evaluate arithmetic expression and let me know your D value if X equals to maybe 5 and Y equals to 9. And make sure, write on your piece of paper and make sure that you use the stack evaluation. Okay, don't do the calculation directly. I know it's quite easy to calculate it, but you should use the stack evaluation and make sure to review your stack. And this time is push 2, push X, right? You will have the stack. You can push 2, push X, and subtract and push Y, push 5, add, and multiply pop D. Pop D means you want to pop the value from the stack and write into the memory. So the memory, you will have X memory, you will have Y memory. So address is X and address is Y. Then you have another address for D. Okay, so you can try and give you 5 minutes. Okay, now I got 4 students down, so I can move forward. So here is the things we do. So we have the memory. So when you do push and pop, actually you deal with the stack with the memory. So we have memory, which is X is 5 already stored in the memory. Y is 9 is stored in the memory. So X and Y is the memory address. You can treat it like a variable. Since we have already done the assembler, you know that it's already assigned the memory address for X and Y when you do the stack evaluation, right? So this time, when you do the stack evaluation, I can push 2, so you will push 2 there, push X, you will move 5 to here. And sub means you will pop 5 and pop 2 out. Okay, pop 5 and pop 2 out. And this time, make sure that the first pop will be the second value. So it's minus here. So the first pop will be 2. So 2 minus 5 is negative 3. When you finish this one, you will push it back to the stack. And the push Y means you get 9 there, push 5 there, and add. So your 5 will be the next one, and the first one is add. So the first value is 9, so you do is 14. Then multiplication. So multiplication will be, you pop this 2, so 14 is the second, times negative 3 is the first one. So negative 3 times 14 will be negative 42. Then you pop D, so means you will pop the value, this guy, for negative 42 goes to D memory. So this is the D. So move this one to the D. So everyone do correctly, does correctly. Okay, so this one is associated with the memory. So you have stack, you have memory, so you associate stack with memory. Finally, when we deal with the RAM, so one more sentence for the things is, for the RAM, actually you need one thing is called SP. So this pointer to tells that where is your stack start. Okay, so this guy will tells you where is the stack start. Okay, so later when we deal with the memory address, then we will look back. So still remember we have some pointers say SP, LCL, still remember in our assembler? Still remember this? We have 5. Still remember this one? This, that, SP, LCL, something like that. Still remember? Kind of, right? Saying, yeah. Now you will see that last time in the assembler, I say that, okay, we will discuss later, right? Now, this time you see the first guy. Okay, so SP is used for the virtual machine, and this virtual machine is deal with the stack, okay? So this is the stack associated with the program. Okay, so next. So we will finish this class. I don't have enough time, so here is 11:30 now. So I will not evaluate, let you to evaluate, but it's the similar. So the similar things is if we do the logical expression. So X and Y, X is 12, Y is 8. So this one is a logical expression. X is smaller than 7 or Y equals to 8, I will let it true, otherwise it will be false. So this one is the if statement. So if statement, I don't want to push the value or pop the value to the some memory address, but it will be used in the if statement later when we do the program control. We will use this stack values to do. Okay, another word, I should say that even you deal with these Boolean expressions here in the hack machine, it will give you true or false values. But later, when you deal with the real computer, it will just give you 0, 1 or 0, -1 to show true or false, okay? True or false can also use the number to represent, but here, to be clear, so we use true or false to represent its Boolean expressions, or use the number to say that this one is the arithmetic calculation, okay? So, or arithmetic related things, so related to number. Okay, now let us start. So push X will get 12, push 7 will get 7. So you have compare less than, so it will compare. 7 is the second one, less than. Ask 12, is it 12? Does 12 is 12 smaller than 7? The answer is false. So you will put false into the stack. And the push Y is 8, so 8 put into here, so you have 8, and push 8, so equal. It asks whether 8 equals to 8 or not, so the answer is true. So then it will be true or false, then this one will be true, right? So true or false, it will be true. So this one is the Boolean expression. So actually you can see that if I give you is the arithmetic expression, you can calculate the value. If I give you is the Boolean values, so it also can do the same. So, okay, last word associate today's class. So this is the actual Boolean and arithmetic one, except this one is accepted by the hack machine. So you can add and sub. So you cannot do multiplication and division for the hack machine. And we have negation. So we can negate it. So negative y, right? So you don't need to write 0 minus y, but you can directly do negation y. So this one is a 3 arithmetic one. And then the remaining is Boolean. So you can do equal, greater than, less than, x and y, x or y, and not y. So this is 3 Boolean. So connector, this one is a compare with values, right? So it's 2 values. So make sure when you do arithmetic, you will do the choose complement. So if you do and or not, it will do the bitwise and or not, and you will use the stack to evaluate your arithmetic or Boolean command. So that's all for today's class. Any questions?